So the way we'll do that today is by looking at a number of different tools and best practices that together build a cohesive end-to-end developer experience where each individual piece provides value by reducing the overall level of effort needed to maintain an open source project. There's a lot to cover, and we're going to go fast, but I'll have a GitHub link with everything that I talk about at the end of the presentation. So let's jump right in with the foundational pieces that every project needs in order to function within the greater Python ecosystem. First up is project metadata. This is a core requirement to publishing and distributing packages on PyPI, and accessible metadata can also enable developer tooling to better understand our project beyond just the files on disk. The best way to do this is with well-structured and standardized metadata. For anyone who's been around the block in the Python world, starting a new project means writing a new setup.py. You import setup tools, you open the README file, fetch a long description, and maybe we'll just find another project and copy-paste. We should stop this. This is not metadata, it's arbitrary code that needs to be run every time the package is built from source. Nothing there is standardized beyond whatever setup tools does. So what we want is a well-defined format that doesn't involve executing someone else's code. Thankfully, we've approved standards focused on a single file at the root of Python projects called pyproject.toml. This file acts as a central location for project metadata and configuration for developer tools alike. The original standards for pyproject.toml were focused around the selection of build backends, the tools that actually transform your Python sources into installable distributions. Together, PEP 517 and 518 define the build system table, which any package manager can use to install your preferred build backend and then actually build and install your package. I'm a fan of Flit, so here we have the Flit core package as the dependency and the associated build backend. But these days, our pyproject.toml can also include standardized project metadata thanks to PEP 621. This new format of metadata is in the top-level project table of our file and includes all of the basic package information that previously lived in setup.py or other backend-specific configurations. This unlocks a great potential for developer tooling to understand and use package metadata without the need to support many different formats. At the top here, we have the basic metadata about the package, as you might expect, including the minimum Python version requirement. And here we have our list of package dependencies. But just listing them isn't often enough and can cause a number of bug reports from users who want to use your project but have different versions or older versions of those dependencies or on platforms where they're not supported. So let's look at how we can better define those dependencies and how that can help guide users and their package managers towards optimal choices. So one thing is that things change, especially in software. Packages will get new features, deprecate functionality, or just outright make breaking changes at will. That's why we can set version limits on our dependencies to make sure package managers install compatible versions. If we wanted to absolutely guarantee compatibility, we could pin our dependencies to exact versions. But that's not convenient for users, especially if another package wants to pin to a different version. So even if we expand our limits to anything with like a major version, we're still potentially leaving users on old versions open to bugs and security vulnerabilities. Instead, we can compromise and specify future-friendly version limits on our dependencies. With this method, we provide only a lower bound on those dependencies, ideally chosen based on the features we use from them and what versions support those features. And our metadata could look something like this. By skipping the upper version boundary, we're trusting that our dependencies won't suddenly break compatibility. That might be a leap of faith, but this trade-off allows our users to upgrade and never potentially get newer and more secure versions. It also means we don't need to release a new version of our own project every time one of our dependencies gets a major feature. And we can always come back and add an upper limit later if we really need to. We can also add environment markers to our dependencies for packages that only need to be installed on specific platforms or backports that aren't needed on newer Python versions. But once we set them, how do we know our version limits are correct? Well, the honest answer is that we need to validate them, and we need to test this on every version we're allowing. But if we're being generous in our limits, that's a lot of different versions to test with. Well, my coworker Tim wrote a tool to help with exactly that problem. And because the Python packaging ecosystem makes him so happy, he called the tool Pessimist. What it does is quite simple. It looks at your project dependencies and runs whatever test you prefer on all of the matching versions, then generates a report on whether your limits are valid. There's also a fast mode, which limits the testing to both the oldest and newest matching versions, specifically for use in local testing or CI when compute time is otherwise limited. Here, we're running it on a project's test suite, and Pessimist validates that it passes with our limits. Now that we're confident in our metadata and dependencies, let's focus on building a reproducible development workflow. Not only can this simplify the process of developing, testing, and validating our changes, but it'll also make it that much easier to replicate our development environment on new machines and VMs, as well as for new developers to pick up our project and immediately make progress and have confidence that their changes are working. But just having a list of commands to run isn't really helpful. You need to have a dedicated command runner. This will combine all of your build and testing steps into a single command, including any preparation or setup necessary to get your project running on a new machine. At a bare minimum, this can be satisfied with makefiles, and I've personally used them with many of my projects for the last decade. But it knows nothing about how Python projects work, and it requires you to re-engineer every piece of the puzzle. Ideally, we want something that can do more of that work for us, especially around setting up virtual environments and installing dependencies. And we would like to do that on multiple Python versions with a single command. Tox is one of the most widely used projects for testing, while Nox provides an alternative system that lets you define your workflow with actual Python code. But today, I'd like to introduce a new tool I created, a rapid development assistant that I called Thanks, or THX. It uses many of the same basic concepts, but focuses on optimizing the development workflow for Python projects. Thanks is configured entirely in your PyProject.toml, and defining simple jobs is straightforward, with a list of job names and associated commands. We can then define a subset of those jobs that should be run by default. Now when we run Thanks, it executes the default jobs in virtual environments and outputs results to the terminal. If everything is successful, we see a bunch of green OK messages. But if one of the jobs fails, we get clear error output, along with the exact command that was run. By default, Thanks will just run jobs using the same Python version that Thanks is installed with. But if we're trying to support our projects on multiple Python versions, we want our tools to run our development workflow on each of those supported versions. Well, Thanks can do this, and it can do it fast. We can simply give Thanks a list of the Python versions that we care about, and Thanks will look for these runtimes when executing jobs. Each of the requested jobs will run on each of the Python versions in parallel with separate virtual environments for each version. In some cases, though, like formatting, we might only need to run a job on a single version. There's no need to format our code base 4 times, so we just mark the job with once equals true. For more complex jobs, we might want to run multiple steps. Here, we define the job as a list of steps, each with its own command to run. Thanks will run each of these steps in order, stopping early if a step fails. But in this case, none of these commands depend on the results of the previous one. They could all run in parallel just fine. So we just mark the job with parallel, and Thanks will run all of them at the same time. And it will run all of these in parallel with each and every Python version that we're testing against, taking full advantage of modern multi-core systems and making our iteration that much faster. But Thanks has one more trick up its sleeve: a watch mode, where it can wait for modifications to our project and automatically rerun its jobs every time our files change on disk. It's perfect for running in an IDE or terminal alongside your code, and gives us immediate feedback when something has broken our test suite or failed coverage thresholds. And its parallel performance provides tremendous leverage for validating our project throughout development. If you'd like to know more about Thanks, please check it out at thx.omnilib.dev. There's more documentation and configuration options that you can find there, along with some recipes for common use cases like code coverage and CI, and how Thanks can help. So now that we have the tools to build out our workflow, we can begin looking at how to improve our development experience. One of the best areas to focus on is code quality, where the side effects of better code are often as important as the code itself. Better code doesn't just mean that our project's faster or more reliable, but also that it's easier to read, easier to understand, and easier to debug. Together, this means you'll spend less time maintaining and more time building. So where do we start? Well, let's pick the lowest hanging fruit first, code style, and let's get the flame wars out of the way. I don't care what your code looks like, as long as it all looks the same. Consistency and predictability are the primary factors to making code easy to read. And the easier code is to read, the easier it is to understand what it's actually doing. Just don't make it my problem. Nobody wants to spend an hour fixing a bug only to get nitpicky feedback about code style. Choose a code formatter that enforces your preferred style and make it an integral part of the development workflow so that nobody, including you, has to ever think about code style again. The more automated and extensive, the better. We want to dump code from our brain and let the computer worry about making it look right after the fact. But really, you should just use Black. It's an excellent tool with strong safety guarantees, so you can run it on your whole code base without worrying about breaking anything. And for anyone who cares, it makes your code look like this. But more importantly, its configuration looks like this. When you decide to use Black, all the opinions come baked in. There's no more debate. There's only one color you can paint the bike shed. That's the easiest tool you'll ever configure in your life, and everyone will either thank you for it or be really angry that they have nothing to argue about anymore. So Black will make your code look consistent, but it won't move your imports. I know a lot of folks really like their artisanal, handcrafted imports broken down by color and size and favorite musician, but that's a lot of work, and I'm lazy. So like code style, it's an awful lot easier to just let the computer do it for you. And this is where I get to shamelessly self-promote some more and say we should all be using usort. It was built from the ground up by Tim and myself to understand and manipulate the syntax tree directly so that it can recognize and make intelligent choices about when and where it's safe to move imports. So in the best case, usort will follow the most common patterns and sort something that looks like this into this. Groups for the standard library, third-party, and first-party imports. This is the easy part. Now suppose we want to import a module and change our runtime configuration before importing something else. Unlike other import sorters, usort focuses on making safe changes, and it treats intervening statements as barriers when sorting blocks of imports. So the async IO import would never move above the simple filter call, and the warnings import would never move below it, maintaining functionality without the need for ugly or error-prone comment directives. This level of safety is what allows us to run usort at scale inside Meta. Every Python file covered by our formatter gets sorted by usort without exception, and we automatically apply catch-up formatting for all covered files every morning. Now, it's great to have these tools, but running multiple formatters separately is a recipe for minor conflicts, which can cause annoying failures in CI or pre-commit hooks. What you really need is something that can perform both formatting and import sorting in a single atomic step. And that's where uformat comes in. Uformat is a combined code formatter and sorter, built on top of Black and usort. Each file is sorted and then formatted in memory as a single atomic step, guaranteeing consistent results in CI and pre-commit hooks. And if any of that sounds interesting, please check out the project's documentation for more details on how they work and how you can integrate them in your developer workflow. So now that we have formatting taken care of, let's look at how we can apply tooling to actually make the code more reliable by finding and pointing out bad practices, subtle bugs, or edge cases that aren't obvious, no matter how pretty the code looks. The easiest place to start is with a linter. They can help you find potential bugs in your code, or even help prevent you from introducing bugs in the future by steering you away from problematic patterns. There are a number of good options in the space, including PyLint and PyFlakes, but my personal favorite, and the one we use at Meta, is Flake 8. It provides a nice wrapper around PyFlakes, has sensible defaults, easy configuration, and most importantly, has a number of excellent plugins available that increase the scope of problems that Flake 8 can help us find. By default, we'll get warnings that range from pointing out bad practices, like star imports, to bugs waiting to happen, like shadowed imports or asserts with parentheses, or even runtime errors like undefined variables or invalid grammar. With some extra plugins, we can also get notified when we accidentally leave debugging breakpoints in our code, or when we use mutable default values for function parameters, or help guide us to better usage of list comprehensions or generator expressions in our code. Preventing bugs before they happen will save future you an uncountable number of headaches and hours wasted debugging your projects. But what you don't want your linter fighting with is your formatter. We recommend turning off most, if not all, lint errors related to code style, and just let the formatters do their job. If it's good enough for the formatter, it should be good enough for your linter. While linters can look for patterns in individual pieces of your code, the real meat is in static analysis tools, especially type checkers, which look at your code base as a whole and make sure everything is correctly passing and using values. And it can do this based on what it knows about not just your code, but other code as well, including the standard library and any other type annotated libraries used by your project. So let's look at an example of how types can help us find real-world bugs that a human may never notice. Let's assume getPath is a foreign API. We don't really know, shouldn't really need to care about how it works. Do you see the bug? Do you have an idea of what it could be? What if we add some type annotations? We're adding new information here that previously we might have needed to read a doc string for. Well, maybe some extra inline annotations help. What if I told you that open raises an exception when passed none? Well, there's some input that can cause getPath to return none, and then we're just passing that straight to open. And you end up with an angry bug report because someone crashed their production service. But our type checker can find and report that before we ever release the code, let alone run it in production. But beyond finding errors, there are benefits just to adding type annotations to your own modules. Consider it as a form of validated documentation for you and everyone else looking at your code. Given these two definitions for the same functions, which one do you find more useful? Which one could you evaluate faster when looking at a foreign API? We don't even need to see a doc string or look at the body of the code in order to have a good idea of the contract being described. This is valuable documentation for developers. And unlike a doc string, a good type checker will force you and everyone else to keep this information up to date. So again, there are multiple good choices here for type checkers, but I recommend the use of MyPy for open source projects. It's by far the most popular type checker available and works really well with minimal setup or configuration needed. For many projects, this is the only option you need, just because there are still a large number of libraries out there that don't have type stubs or aren't appropriately marked as annotated, and there's not much we can do about that. You don't even need all of your code to be type annotated to start seeing an impact. But if you're willing to type annotate everything, including your test cases, I highly recommend enabling strict mode. This will let MyPy get more pedantic, find more bugs, and also point out any time you fail to annotate your code. So speaking of documentation, while looking at the code directly is important for working on your own project, the last thing you want to look at is someone else's code, especially when you just need to know what a function's called or what various arguments do. Most importantly, there will come a day when your own code looks foreign to you, and you've forgotten what all your own APIs look like. When that happens, you can turn to your own documentation for help. But we don't just want to brain dump info into a text file, tucked away and forgotten, cursed to never be accurate again. What we need is tooling specifically designed to extract as much information as possible from our code base, including doc strings and type information, and automatically compile that documentation into useful formats. Now, there are many different tools that can do this, but Sphinx is designed specifically for Python and is used by hundreds of open source projects. Sphinx will compile and transform a set of source documents into a full website, including navigation and text search. You can add arbitrary pages as well, allowing you to build a combined project and documentation site all in one with relatively little time effort required to maintain it. Sphinx uses restructured text format, similar to Markdown, but focused on technical documentation. When compiled, Sphinx generates well-formatted HTML, and we can include code blocks with syntax highlighting, links to other sections of the documentation, and much more that isn't possible in plain Markdown. And we don't need to sacrifice the ability to read and understand the source text in an editor. But the real magic of Sphinx comes from the Autodoc extension. This gives Sphinx the power to look at your project's source code and automatically extract module, class, and function APIs, including type annotations, docstring, contents, and more. With this in mind, we can actually write our doc strings with the Sphinx results in mind using inline restructured text. We could include references to other functions, inline code blocks, and anything else we could put in a normal documentation page. Then we just add the appropriate Autodoc directives to our documentation and regenerate our site. And now our compiled documentation includes our function prototype, formatted contents of our doc string, as well as type information. Now you might be asking, what can you do with this once you have it? Well, maybe you've heard of a little site called Read the Docs. This is an excellent free service for building and hosting your project documentation sites, and it's specifically designed to work with Sphinx. It also has excellent integrations with GitHub, including the ability to automatically build every time code is pushed, as well as building preview sites for each pull request, so you can easily evaluate any documentation changes for PRs. So now that we have end-to-end developer and documentation workflow, let's take a look at how we can streamline the process of community contributions without putting undue burden on your own time. One of the most important pieces of having positive community interaction starts with setting clear boundaries on expectations in both directions. You really should have a code of conduct. If and when your project gains more attention, clowns will inevitably show up. And the easiest way to deal with them is by having a code of conduct with a clear set of rules and consequences that you can follow. I use the contributor covenant at the Omnia project and recommend it both for the standards it includes as well as their guidance on how to enforce it. Beyond that, make sure you set clear expectations for what contributions you're willing to accept from the community. If you only care about bug fixes, say that. If you're happy to take feature requests, say that. But let folks know ahead of time if they should open an issue or discuss new features before they take up their own time and yours with pull requests that you would never accept. If you can, document the level of support you'll give for each project, but don't overcommit yourself. Unless there's a paid support contract, you do not owe anyone your time, you don't owe them your energy, and you certainly do not owe them your sanity. If someone's being too needy and is taking up your limited time, then just dump them. If they're being nice, apologize and just tell them you can't help them, maybe point them to a different project. But if they're being less than nice, just don't engage and remove them from the community. Don't waste your time on unproductive community members. On a happier note, let's look at how we can simplify and automate as much of their contributor workflow as possible. We want to remove barriers between the community members and their ability to ramp up on your project, because the less friction, the more likely you are to receive high-quality contributions. This starts with, you guessed it, more documentation. A basic contributor's guide starts with the steps to set up and build your project from source, as well as how to run the project and test suite. A better guide also includes extra validation steps needed, like linters or formatters, as well as general guidance on what to include with changes, like documentation, test cases, or changelog entries. This is where a reproducible workflow from earlier can really help. The closer contributors get to the workflow you use, the more trust you'll have in their contributions, and the more trust they will have in their own changes that they're making during development. You can further help guide contributors in the right path by adding detailed issue templates and pull request templates to your project that will pre-populate the text boxes with whatever you want. You can have multiple different templates for specific types of issues or requests, but be sure to include any spots for specific information that you want to see, like steps to reproduce, the user's environment, or whatever makes sense for the project. Once your community members have submitted a pull request, you want to make sure that you automate the testing and validation process in a way that not only reduces the time you spend reviewing their contributions, but also gives immediate actionable feedback to the contributor themselves. Continuous integration systems are one of the easiest and most common ways to make this happen. If your project's on GitHub, then GitHub Actions is the easy choice and runs for free on public repos. The biggest benefit here is the ability to configure CI to test your project on a variety of operating systems and Python runtime versions, and get direct feedback in a pull request on which of those pass, so you can easily see if it's OS or version dependent, or if it's a more basic issue. Again, we'll beat the drum for reproducible workflows. Whatever CI platform or system you choose, it should be configured to use the same build, test, and validation workflow that you use locally. This will help minimize surprises and make it that much easier for you to review a pull request and understand the results of the CI. Lastly, be aware that GitHub Actions, as well as integrations to other services, are available and can also improve the amount of time that it takes you to actually review a pull request. The last piece of the puzzle is releasing your project. The easier it is to prepare and release a new version, the faster we can publish our bug fixes. And the more boring each individual release is with targeted fixes or improvements, the more reliable and trustworthy your project will be perceived. So let's start with the most important part of releasing new versions, picking the right version numbers. Ultimately, we want version numbers that convey some amount of meaningful information, like how big or how important or how dangerous your change is. One of the most well-known schemes is SEMVer, or semantic versioning, and I'm here to say SEMVer is impossible. The major version number is supposed to tell us when breaking changes occur, but how do we define breaking changes? Is a change to a feature breaking? Is an API change breaking? Is a bug fix breaking? On the other end of the scale, we can simply base our versions on the year and date of each release, but beware, because once you make your major versions based on the calendar year, you've just burned more versions than Chrome. Yes, technically you can increment a version epoch and start over from zero, but literally nobody wants that, and you'd be surprised how many tools will break. So really, just pick something, be consistent with your versioning, and communicate your plan clearly. But picking a version number is only the first step. There's a lot more that can go into release than you might expect, so we want to automate as much of that process as we can as well. And like our development processes earlier, we want to have reproducible workflows. You shouldn't have to figure out and piece this all together every time you get a new laptop. At the very least, document the necessary tools and steps to publish a release so that future you can just refer to your documentation. But we can do more. The key to reproducible releases is basing them off of published tagged revisions in your source control. And those tags should already include any changes to documentation, version numbers, etc. Now, once it actually gets to getting that, the tools can help. I specifically wrote a tool called Attribution, which automates the process of generating a changelog. As for building your actual release, you want artifacts, but we're running out of time, so I'm going to power through this. Wheels are binary wheels. They're only on specific platforms and versions. Source distributions are what you can actually rebuild on anything. That is key. You want your SDIS because anybody who's on a OS or version where you don't have a wheel can actually build your project. But you want the combination because it's faster for most users. And if you want help in building all of those, the CI build wheel project can help automate a lot of that in your CI steps. And it helps you support that whole matrix of version compatibility. So phew, we made it. We've reproduced our workflows, we've improved our code quality, we've fostered our community, and we've published our distributions. Well, now we take time for ourselves. Don't forget the golden rule. It's your life, your project, and ultimately, you're the only one who can choose how to spend your time. I appreciate you spending this time here with me. And if you can find links to all the projects and resources on my GitHub repo. Thank you so much. Have a good PyCon.
Thank you, John.